talking about how far the Roman chronic will get us on the way to HWO.
Yeah, so obviously that's a loaded question, and I don't pretend and I have 10% of the answers here, but it's just to get the discussion started. A very short talk because on one side we don't really have technical or scientific requirements for HWO yet, so we don't know what we're shooting for exactly. And on the other hand, the TVAC results that were obtained with the Roman coronagraph aim to meet minimum requirements. They were in some cases stopped a little bit early rather than performance limiter, so we don't really know what performance ultimately we would have had in TVAC. And then on top of that, the in-flight results may also, of course, differ from the TVAC result. So two moving sticks here and trying to compare one to the other, but not being facetious, we do have some knowledge of the Roman coronagraph elements and their performance and functionalities. We've seen a lot of that during the last 2 days, so we can, still have a look at some kind of CBEs and some TVAC levels of performance. So I'll show some of that. And on the other hand, on the HWO side, we also do have a reasonable idea of HWO's minimum requirements. Some of them came directly from the, of course, 2020 decadal. Some minimum requirements in a way, or range of requirements came from the lengthy HWO and HWO studies, pre-decadal studies. There's also 2 papers that I will invite you to have a look at, which are discussing some possible HWO-related requirements for exoplanet science, one by Chris and one by me, and with a lot of co-authors that just got actually accepted for publication in JADIS last week. Come out soon. And then of course we got the TVAC and CBE performance. So in a way, what we are trying to do here is to kind of upgrade this paper that we published, a bunch of us 4 or 5 years ago now, 4 years ago, I guess, which was already trying to understand how the Roman coronagraph would pave the way to what we called at the time future missions, because we didn't have one identified. So now we would have to replace it with paving the way to HWO. Finally have something real to on the horizon to compare to. And it was the same kind of approach. We would like have a look at how far the Roman coronagraph would go towards HWO or HWO at the time. We had different CBEs, we had different design specs. So this needs to be redone and upgraded, and invite the community to do that. I want to do it again, but I'll try to do it here a little bit. That's a quick snapshot at how the top level characteristics of CGI and HWO compare in different areas. And the color coding here is whenever this is blue, we're pretty much in family, meaning that either the CBE or the TVAC performance is in line with what we think we would need for HWO, or the range of what we think we need for HWO. When it's red, it means we're a factor of 10 away. I think I have also orange, which is like a factor of 3 away. And all of this is very qualitative, but that gives a visual of how far we are in some areas. So I'm not going to go through all of these. All of this is going to be available online. But the main thing that we know and that hasn't changed is that when you just look at the high level performance in terms of raw contrast and detection limits, we're quite far off in terms of what would be needed ultimately for exo-Earth characterization for HWO. However, when we look at the subsystems, we find a different picture, and I'll show that to you next. In our working angle, we get down to about 3 lambda over D with HLC. We're going to need probably 2 to 3 lambda over D for HWO. The 5 sigma detection limits, for TVAC is 2.5 10 - 8. For CBE, that might be around 5 times 10 - 9. For HWO, it's somewhere around 10 - 10 TBD, and so on. So you can see, spectral bandwidth, we're not too far. Spectral resolution, we're in the bulk, or maybe we're going to need a factor of 2 higher. There's also much higher spectral resolution that's being explored right now. And see whether that would be useful or not for HWO. But unless we go to that median, much higher spectral resolution, we should be working at around 100, and we're at about 50 right now for CGI. The types are different. ConOps might be different. The spectral subtraction method, the last one at the bottom here, kind of interesting because we're going to try RDI and ADI with Raman. So we're going to get a lot of data on how well that works or doesn't work, what the limitations are. I think that's going to be interesting. For HWO, we have a range of possibilities. I may have missed some here, RDI, ADI, spectral differential imaging, coherent differential imaging, polarimetric differential imaging, spectral estimation using wavefront sensor data, which is something that might even also be able to try and entertain with Raman. So as I said, going into the subsystems, now the picture is a little bit different. That's why you see that a lot of these TVAC results or current best estimate of CGI performance are actually a lot more in line with what we would expect the requirements to be on HWO. A big caveat here is that for many of these HWO requirements, we don't have detailed numbers yet. So what I did is I took the range of the HWO and HWO requirements for each of these numbers here, and that's for a visible coronagraph, V-band coronagraph on HWO. Just here, we may want to observe a different wavelength. So what you can see is that we've heard a lot about this low-order wavefront sensor results, the sensing errors from TVAC, which use the OS10 observing sequence. We got the CGI CBE, which are using the OS11 observing sequence, and I asked John and Anas why did they use actually different observing sequences. And the reason is OS10 actually had a better time resolution than OS11, and the levels of wavefront perturbations was 3 times higher. Right? So that was actually a worst case scenario to use for TVAC. So when we injected perturbations, the PACE team used to use these OS10 simulations. So even though we are using higher wavefront errors, the TVAC results for the low-order wavefront sensor were really good. And they are kind of in par with the CBEs for the most part. How much contrast fluctuations did we get from higher order? Really know. Well, in terms of wavefront error, we don't really know. In terms of contrast, what we observed over 5 hours with the loads going on, right here, was about a 2 times 10⁻⁹ contrast degradation. Also using OS10 and trying to correct for the wavefront error that were introduced following an OS10 time series of wavefront aberrations. Number of DMs, we don't really know how many channels we're going to get for HWO. But we're probably going to need at least 2 DMs per channel, and by channel I mean channel that could work in parallel at different wavelengths or different polarization states. So the number of times we multiply the CGI layout, if you will. We got 3 channels at 6 DMs. DM's format is a big question mark. They range from 48 by 48, which would be great because that's what we are already demonstrating on Raman, to about twice that size. To the last ones, maybe one that's kind of interesting is the number of dead actuators. Right now we have 1 on DM1. We got lucky at what's shown before. It doesn't fall in that most sensitive region of the DM. How many can we tolerate for HWO? That would really depend on the map design. I can't tell whether 1 would be acceptable or not, but pretty close to 0. Last set of subsystems and functionalities that we have on CGI and how they might relate to HWO. We will likely use very different coronagraphic masks on HWO than I would say the still 1st generation kind of mask that we're using on CGI. These are masks which intrinsically are fairly lossy, even if you take into account the aperture, which is not very friendly to coronagraphy. It's binary based, amplitude based, shape pupil, so you lose some photons. I think we're going to want likely higher throughput masks for for HWO. Yet, all of these masks have been modeled, manufactured, and characterized at the right level that we would want for HWO, the met tolerance. So I think there's a bit of both here, of relevance and not relevance. That's why I put this as orange. I think we've shown the ability to manufacture and characterize these masks as we need. The precision alignment mechanisms that came from PIA had remarkable translation accuracy. Not sure how much more we're going to need for HWO, but I think it's in family. The detectors, I mean, Nathan showed the results that they got are pretty impressive in terms of shielding, etc. It's going to be really interesting to see how well these MCCDs are behaving over time in orbit, and will comfort us in either staying with the MCCD or shooting something out. The detectors format is also in family, and the noise properties, I'm not going to go through all of them, but they are also very much in family. So there's going to be a lot of interesting findings here with the detectors as well. Can't really see this here, but on this plot, I'm going a little bit more onto the science side. I mean, that first part was really about how relevant CGI will be technically. And then, there's how relevant will CGI possibly be scientifically. And we've all seen this plot many times, which shows where, the currently detected, directly detected planets lie in a contrast versus separation diagram, and where Raman is going to fall. So our only requirement was to meet the detection limit at 10⁻⁷ between 6 and 9 lambda over d at 575 nanometers. But we have demonstrated in T1 that our detection limit at greater than 2.5 10⁻⁸, and our CB is around that curve here, around a couple 10⁻⁹, maybe 3-4 times 10⁻⁹. So I think it's likely that our detection limit falls somewhere in between, at least for HS. And what you can see here is that for mature planets, so older planets around mature stars, we're barely going to skim the top of the exoplanet population. So we might be able to detect a few, may be able to get spectra of 1 or 2. But the thing is, it's a very discontinuous landscape in the sense that you really need to reach a threshold performance before you really have access to all of these planets. Remember, the Earth is here. And we know that a lot of these extrasolar systems have lots of some Neptunes, etc. So we're going to have a lot of planets covering all this space here, and we're going to just look at the top of it. So, and that's the reality. Even though we get 10⁻⁸, very contrast, which is exceptional in the visible, that doesn't get you a lot of this mature planet. We get some of the luminous ones. I'm just insisting on this because the situation for disks is very different. For this, you have now a continuous set of disk opacities and relative contrast. This, I'm going to go all the way from here to there. And so even at 10⁻⁷ or 10⁻⁸ contrast levels, we're going to be observing new structures at much closer in separations than any other instrument can do in case of light. We're going to enter a new regime of debris disk physics. The distribution of dust and resonances is set by transport phenomena rather than collisions, because these disks are just not dense enough to have a lot of collisions. So I would think that a lot to be done in disk physics with CGI, and in particular, I will of course insist as usual that exozoli is going to be really important in terms of observations coming from CGI to prepare for HWO. I'm not going to go into a lot of details here, but all of the exozoli measurements that we have so far are 10, 11 microns with K-core LBTI, or sensitive 1 from LBTI from 5 years ago. And we don't really know how bright these exozoli disks will be for HWO. They are actually the largest photon noise source for HWO. So I really want to highlight here that we need to do a survey. We'll be able to do a survey of exozodiacal disk with with CGI. I think in terms of preparing scientifically and even technically for HWO, that's going to get us the furthest. So hopefully we can make the time for that. There's a big caveat. We only do that if the performance warrants it. But I think that even at the TVAC level of performance, we'll do better than from the ground by a factor of a few. You can push that 10 times better. It's even better. But the main thing is we're going to do it for the first time at the wavelengths of HWO, visible near infrared. And you can see here in that plot that extracted from a paper by HWO and Douglas that working angle is key here if you want to access the available zone, even the outer edge of the available zone. You need if your inner working angle is 3 lambda over d, which is 150 milliarcsecond, you get 75 of these targets. If you get to 6 lambda over d, which is 300 milliarcsecond, you're down to maybe 10-ish. So inner working angle is everything for exosome. All right, so I'm just going to conclude with some what I consider to be cons and pros of how well CGI can prepare for HWO, and again, that's very qualitative. In terms of cons, we mentioned that already. We are not in the right regime in terms of flux ratio detection limit. We only skim the top of the mature exoplanet population. The aperture is different. One is a monolith, the other one is a segmented primary. So we're going to have to, as we know, develop a lot of technologies and testing in the lab to deal with the segmented primary. It's maybe a simpler, less obscure primary. And the Roman chronograph does not have an IFS. Scope for the reason that we know, schedule and budget. We think that it will likely be an IFS on HWO rather than a point spectrum. Now there are some pros as well. Main one I think is that in fact many of the Roman chronograph subsystems do have performance expected to be in family with the needs of HWO. So forget about the high level detection limit. It's really limited by the type of aperture that we have here. In fact, when you look at pointing sensing and control, low order wavefront sensing and control, the quality of the broadband imaging detector, we are very much in par with what we think the needs are going to be for HWO. And the reason why this is true is because while this telescope is beautiful and extremely stable, it's not very friendly for coronagraphy. And we always joke like putting this little message from our friend David Spargo, which is to say that this pupil will only be found beautiful by her mother. So yeah, many functionalities are also in line. Forget about performance. What are the functionalities available? A lot of them are aligned with the anticipated needs of HWO. I also forgot to quote spectroscopy to some degree and the polarimetry. Of course, high order reference sensing and control, precision optics and masks, precision mechanisms, ultra low noise photon detectors, photon counting detectors. We will test speckle calibration methods in the right contrast regime where both amplitude and phase defects matter. Same regime as for HWO. And as I mentioned before, we'll provide principal unparalleled sensitivity to exozodi at the scattering wavelengths of HWO, and with it the potential for a very powerful exozodi survey if the tech demo performance confirms it and the time is made available, which we just heard of from Julie. And I think that's it. Sure.
That last point is interesting because it will be more sensitive to exozodi than HWO because of the F number. The F number it's a faster telescope.
It's also a smaller diameter, so in fact you get more signal in your diffraction beam.
Right.
But can you do it in 4 days?
Yeah. So not the whole survey. I don't have it. Yeah, I think
But one, just even us.
But so when we looked at this with Johan and John Debs at the time, it would take about a month of continuous observations to do the survey of 75 stars. So in average, less than a day per target. So, over 4 days, we might be able to do a few. Spectroscopy is the killer in terms of time, but if we do broadband imaging, we might be able to do 10 targets.
A comment on the precision alignment mechanism mentioned on page 6, you listed 2 microns. The 2 micron under Roman CGI is limited by electronics.
Okay.
The mechanisms provided by MPA are 10 times better capable for sub-micron.
Thank you. Yeah, that's true.
One acknowledge that their magnitude are electronics. No, actually, we didn't have the money to make new electronics to use the encoder. It's capable of sub-micron.
So it's the
We use the actually Hall sensor on the motor. We're class D technical by saving money. That's a lesson learned.
It wasn't a limiting factor for us. It works for us.
It works for us. Yeah.
Can you remind me what the throughput curve looks like near the inner working angle for?
So the throughput curve is, so it goes up to 4.6%, the core throughput, right?
Yeah.
And it kicks in at, with half of that at the inner working angle of lambda over D for HLC.
But is it like an APLC where it's a step function basically?
Like this.
Okay, so yeah, your disk brightness is going to go probably sharper than 1 over R squared, right? So you'll be able to get closer to
Yeah.
things like this.
Good question online.
Yeah, sure. From Russ. Yeah, I don't know, Russ, did you want to just say your?
Russ, go ahead.
Yeah, Russ, go ahead.
Sure. So first of all, great talk. So my question is, do you expect CGI to help HWO in ways that we do not currently foresee? For example, exposing unknown unknowns, and might this even be the main pro?
I don't know about the unknown unknowns. I could say, yes, you're probably right. I mean, that's what we always find with all of these telescopes. But I mean, not kidding. Yeah, there's a lot of things that we're going to learn that we just don't know that we're going to learn, and it's just hard to know what that's going to be. But
Question is, based on past experience, do tech demos often find a lot of unknown unknowns, and is that where a lot of the value lies?
understand the question to learn about lead Pathfinder.
Yeah, we can certainly talk about this a little bit more broadly, I think at the open section at the end.
Yeah.
Because Russ, I'd love to hear your ideas of, in my mind, it's a really question for the CGI team about how well we can characterize down to levels to uncover the unknowns at the level that we need to, right? Bertrand's chart showed only 4 red bands of areas. Now, of things that are different from HWO, right? Now, we can confirm a lot of these things are true, right? We can say that a lot of these things will translate directly and that could be part of our, but as far as trying to understand what will get us to the future in those hard areas.
My question was sort of along these lines, or comment for you, Bertrand, which is, I wouldn't underestimate how much you will learn about environmental effects. Micrometeoroids for sure, because you're actually, which raises questions for me about, what kind of diagnostics you have for pupil imaging to understand the micrometeoroids and then put that in a model, compare it to the hits, see the effects on the DM correction, all that kind of stuff. Radiation effects is the other one. The unknown unknowns typically are the things you can't test on the ground. Try and test as you fly, but you can't test environmental effects. And almost every flight mission I've ever been on, it's been the environmental effects that bite you. You can look at Chandra, Stis on Hubble, and buildup of hot pixels, degradation of radiation, those kind of effects I think will be super interesting.
Yes. Yeah, we can model what we want, but see exactly what it is.
But that's why it's critical that we don't just look for a year. The time evolution of, even the DMs, I'd be interested to see how stability of the DMs changes over time. We want to, we spend all this money, let's mine it for as much as we can.
Yeah, so related to that, there's this Zornicki reference sensor. So can somebody remind me what's the spectral frequency? So it's looking at the pupil plane image.
38 and a quarter pixels across.
How many pixels?
38 and a quarter.
Okay, so it's almost 48 by 48, almost. No.
No.
You don't have, well, 48, it's not that far. So it's almost like an actuator and a half. or something like that. That's weird that it was not chosen to be 96 by 90.
So this would be even worse than it already is if it was more pixels. So.